Okay, thank you very much. Thanks for coming and thanks for the invitation. I've given this version of this talk in 3 languages, and from elementary school kids to now scientists. So I hope it's not too elementary for you. I'm a mathematician, so this has been kind of every time I prepare a new version of the talk, I learn something new. So I hope, and I think I do it because it's interesting to me and it's fun. So I hope it's the same for you. I hope you find something there that you probably didn't know and that might be interesting. So let's just start with a little bit of history. So games that have to do with the ball are ancient, as you could see, in ancient Greece. I was always fascinated by what happens with a game which nobody seems to know exactly what it was, but it seems everybody agrees that it was pretty violent, and maybe players did not survive the game. This is in Central America, so we have things of this sort that point to something about the game, but I think it's not clear exactly how it worked. People believe that was like the goal where the ball maybe had to go through. This is an actual field that still is there. There was also various other things that I found that I didn't know about that I thought they were pretty funny and surprising. So there's something in France called La Soule that the first record goes back to 1100. And it was somehow some kind of crazy game where something like a ball had to be taken from one side of the field to the other. But people got limbs broken. And, so it seems to be some sort of chaotic semi-war. So the next thing that I found that kind of closes that chapter is this actually prohibition to play this game, and in 1800. So it was something in I think in Normandy, and it says, I don't know if you can read it, but it basically says something like, we decided we're going to ban this game because it's simultaneously contrary to humanity and good order. So these are somehow the sort of proto-history of soccer or football. People don't get limbs broken that often, but it's pretty violent still. Anyway, this is how things might look like early on. Mostly male, only male. Then things changed over time. Also, not just white Europeans playing, and others as well. So let's start with the actual football. So the title is about the actual ball. I mean, but for some reason I was following more the English form of it than the American one. So if people that follow the World Cup are very passionate, and there's this website which has a picture every single ball for each World Cup. And the thing is that the ball is a big deal, and it's created anew every time. So there's a whole design. I don't know quite how it works, how to decide what ball is chosen, but it's a big deal. So here are the balls. So you can see the range of years is every 4 years, right? So the first one was in 1930. So this starts with the 1934, which was in Italy, and up to 66. So I asked this question to high school, elementary kids, but maybe it's also, I'll also ask you. So this is one page. This is the next page. 1974, 2002. So what's the difference? This page and this page. Come on. Eh? The tiling is certainly, you're a geometer. That's the first thing that strikes you. Yeah, the tiling, which is a little bit what we'll talk about. But there's another thing. Huh? What's that? Advertisement, yeah, true. Something more basic, though. It's so basic, maybe you don't see it. The colors. So what changed? Television. In the 70s, they started showing World Cups on TV. And if you have a ball that is the same color moving around in a black and white TV, you're not going to see it. So you want contrast. So that's how this ball, which is the probably, if you ever you would ask anybody to draw a football, this is probably what they would do. This is sort of canonical one. In fact, I forgot now. There's a slide I found. There's a guy who has YouTube videos of math, who is very funny. He's an actual mathematician, but does kind of as a job entertainer. And he found a picture of a street sign in the UK pointed towards a stadium, and it was wrongly drawn. They were just okay. So here's going into the story here. You see the black things are pentagons, and the white ones are hexagons. And this thing, I forget what it was, but it had 7 pentagons. There's something completely wrong. And so as a joke, he kind of called the public transportation or the public signs, whatever, in the UK, and say, this sign is just wrong. You need to change it. And they said, well, we don't know anything about math, so it's not a problem. And it was kind of pretty funny. All right, so these are, the balls becoming more and more sophisticated. The amount of engineering that goes into them, it becomes really high level. I don't know much about, honestly, I don't really know much about soccer or balls, but I understand that this ball, the Jabulani, created a huge problem because somehow it seemed like it moved in ways that the players had never seen before. And they were really unhappy. So here's the first ball. And this, as it happens, the game was played in Uruguay, the World Cup, and the final was Argentina versus Uruguay, and Argentina lost. So it's a big thing. But so you see pieces of leather put together in some haphazard way compared to this incredibly more sophisticated thing. So what I want to talk about is somewhat of the engineering problem of how you create something that looks like a ball. Okay, so and I'll talk about 3 things that somehow have the same engineering problem behind, which is how to create something that looks like a ball with pieces that are basically as equal as possible and as simple as possible. And you'll see 3 instances where this problem arises, and how do you try to go about solving it. Okay, so let's start with a much simpler problem, which is what happens in dimension 2. You want to create not a ball, but you want to create a floor, something flat. So if you want all the pieces to be the same, you want to take the pieces to be as regular as possible. Well, you take a regular n-gon. And as we all know, you cannot do that with many different shapes. I mean, you can do it with squares, triangles, or hexagons. And as the bees well know, a hexagon is pretty good. But that is not only a sort of conscious choice. This also is a self arranging pattern. There's no, as far as we know, any sentient being that somehow forces the salt to arrange itself like this. This is how do you say it in English? Salt something in Bolivia. And maybe some of you will explain to me, why is it that this happened? It must be some low energy state, I don't know, some equilibrium state of the system that ends up producing this. Well, not, of course, they're not perfect hexagons, but they're pretty close. So if you try to do this with 5 gons, 7 gons, octagons, of course you can't, because you're just going to miss part of the plane. Now, if you introduce more sophistication, if you allow the pieces to be basically arbitrary, but that requires, well, and I will, in my mind, there's equivalent versions of what it requires: information, energy, or time. You need a craftsman to do this. You need thinking. You need more than just pieces that are all the same that anybody can put together. These are pieces of floors in buildings in the Alhambra, which, as you know, is like the mecca of symmetry in walls and in floors and so on. These are other forms. This is something I think a picture I took myself I think it was in the floor in Cologne, in the cathedral. So if you start playing games where you allow much more flexibility, then a lot of other things can be done. And as you know, things like this from Escher. Or if you start with saying, okay, well, how about we don't do anything symmetric, repetitive? Well, then it's a whole new other talk that will be about non-symmetrical or non-periodic tilings and so on. So this is the famous version of the famous Penrose tiling. And this one is another version of the famous Penrose tiling. And this one I like because my former colleague, Lorenzo Sadun in Austin, he works on this, and he was so passionate that he managed to get his when he rebuilt his bathroom, one of his bathrooms, he managed to convince the guy who put down the tiles to actually do this. So this is a picture of his bathroom floor. And he was really happy and surprised that the guy took it as a challenge, and he actually did it, following the instructions. All right, so let's move to dimension 3, which is what we really want to talk about. So I'll talk about 3 things. The football, soccer ball, of course. Geodesic domes. You may recognize this as the Il Duomo here in Florence. And viruses. They all, to a certain extent, have the same underlying engineering problem. How you create things like this, these 3 things, with the smallest, the fewer number of pieces that are as simpler as possible, that is easy to put together. Okay, so again, this is ancient stuff. We know from the ancient Greeks that if you want to do something like that with all pieces exactly the same, then you have very few choices. And these are these famous 5 Platonic solids. As you also probably know, Kepler, a famous astronomer, went a little bit haywire with this idea that these forms were fundamental, and had built a whole theory of how planets are distributed in space by putting these polytopes one inside the other. Not one of the things that he did that survived very well. Now, another thing that I found when looking at this is something that I had not seen before, is there's a bunch of these things, several hundreds, that are found all over Europe, and nobody seems to know what they're for. Okay, so they're made of metal, and maybe they held some fire, something, it's not clear. And this, they find them occasionally in various places in Europe. So this also, maybe the shape was relevant for whatever purpose they made them. It's not clear. And art, of course, is a big part of this. These geometric things tend to be inspirations for artists. So this is actually something that is a sculpture in this place in Ascona in Switzerland. That is you may have been there because they organize schools. Is somehow associated to ETH. And this was either, I think it was in memory of this school of dance created by, founded by this guy. Anyway, these shapes also come in life. Many living creatures have the same type of underlying structures. This is, I'll come back to that with the viruses. So famously, Euler, one of the many things he did was to prove this amazing formula that if you count, if you have something that looks like a ball and you count the number of faces minus the number of edges and plus the number of vertices, the number always comes out to be 2. Here is the original paper in Latin with the formula right there. So the 5 Platonic solids have this distribution of vertices. Oh, the S remain from the Italian version. So be edges. And the one that I will concentrate from now on will be the icosahedron that has 20 triangular faces. Now, these solids have 3 groups of symmetry, and it's only 3 and not 5 because they come in pairs. The tetrahedron being its own dual, so it has only one attached to it. And these groups appear everywhere that you can possibly imagine, and I'm sure you encountered them in more ways than one. But recall that the smallest one is A4, the alternating group in permutations of 4 letters. So next one is S4, so all permutations of 4 letters, and S5. And so the order of these groups or symmetry of these objects is 12, 24, and 60. And the thing I want to highlight at the moment is that the only one that is divisible by 5 is S5. A5. Yeah, it should be A5. I got this wrong. A5 of order 60. It should be A5. So none of the other groups has order divisible by 5, and therefore has no element of order 5, no symmetry of order 5. These are groups of rotations in 3 space. So this is the icosahedron. So we said 20 triangular faces. And this football is built out of, you can think of it as being built out of truncating the vertices of the icosahedron. So here I highlighted 3 vertices. And you think of it chopping perpendicularly to the thing going down from the vertex to the origin. You're going to get a pentagonal face. And because if you do this on each one of the vertices, it cuts this triangle into pieces that a piece that now looks like hexagon. So the end result is that you end up with what is now called the truncated icosahedron, which is our football. Yeah. So it's made out of 12 pentagons and 20 hexagons. 12 because there were 12 vertices, and 20 because there were 20 faces. And these other guys are some form of variance where you now relax the condition of what your faces look like. I think these, you still use regular polygons, but you mix them. And this is something Archimedes did, and they're called Archimedean solids. I'll just move forward from this. Okay, the thing then maybe to highlight is that in this truncated icosahedron, we see a five-fold rotation symmetry on the pentagon face. We see a order 3 rotation, or order 6 should be, and a order 2 here. So chemists call this the 2-3-5 group of symmetries. So the icosahedron, the truncated icosahedron has then these 32 faces that we said, has 90 edges and 60 vertices. And these things also go back, way back. This is a beautiful picture of a truncated icosahedron actually done by Leonardo da Vinci in this book by Luca Pacioli on symmetries of various kinds. So he has several pictures of things like this, and this is the icosahedron truncated. So here's our truncated icosahedron. And if you open it up, you cut it appropriately. You can put it on the ground. And here is since I would be nice to do it in real life, but these days we can do it virtually. So here's how you build up the icosahedron from its flat form. Okay, so the football then is a truncated icosahedron. The 12 pentagons get colored black, the 20 hexagons get colored white, and this is the geometric form. This is what you get if you inflate it and push it into looking like a sphere. And here's again, the standard, so to speak, shape of the football. Okay, so what would be the next thing if you try to create things that look like balls? And again, with the principle that the sort of guiding sort of principle all along what I'm trying to say is that we want to keep the number of pieces small, the shape of them, and as symmetrical as possible, and the fewer of those pieces as possible. So in 1937, mathematician Goldberg came up with this description of polyhedra, so things that look like the Platonic solids, but not with a bit more relaxed conditions. So he looked at the following cases. So we want the faces of the polyhedron to be either a pentagon or a hexagon, and not necessarily regular, just that it has 6 sides or 5 sides. Okay. We want any two given faces. So if you only accept two faces to meet, you're not going to get anywhere. So we want to accept 3 faces meeting at a vertex, but not more. Just 3 at each vertex. And then finally, all of these things are fairly constringent. We want the symmetry of this object to be like the one for the icosahedron. Okay, to have the same group of rotations. Okay, so here is a Wikipedia rendering of this. So this looks like there's plenty of them. A priori, with the definition, you may ask whether there's any. And again, this is maybe too elementary for you, but I'll ask you anyway. Which one is the football? You're pointing. This one? Is it this one? Or is it this one? They look the same, but they're not. Why is that? Right. So we could go back to the ball to see this, but indeed, this one has a vertex like right here that has 3 hexagons that meet. And that doesn't happen in the football. So if it's anything, it has to be this one. And it is, okay. So, so this one is funny because this one, as far as anybody knows, there is no ball ever built that way that is been seen. So you can wonder why. It fails one of the principles in a way because it probably, in terms of looking like a ball, is probably about the same. I don't know. I mean, one would have to what that means. But I suspect that it's probably even perhaps more, if you inflate it, even more kind of better ball looking than this one. But this one has 42 faces. So in some sense, is more complicated than this one. And this one, of course, has only 12 faces, but if you inflate it, you're going to get something pretty horrible as a ball. And all the other ones are variants of the same. They all fulfill the same criterion of the definition of Goldberg. And there's another thing that maybe I should say, that I actually was fooled by this because I didn't pay it enough attention. This is misleading because it looks like all the hexagons, for example, are regular, and they're not. So this is another interesting thing about the truncated icosahedron, that all the hexagons are regular hexagons. They have the same length of the sides and the same angles between them. That's not the case for this one. But you wouldn't quite see it from the picture because the difference in the angles is very small. Okay, so let's just go with this. This is an amazing fact. It's really simple. You can show your nephews and show them how cool you are. All of these guys have 12 pentagons. All of them. No matter what you do, you must have only 12 pentagons, because if it has at least 11. And the proof comes from simply by counting things and using Euler's formula. So let's just go over this quickly. So there are pentagons and hexagons as faces. So the total number of faces is the sum of the two quantities. The number of edges is each pentagon has 5 edges and each hexagon has 6 edges. So the total number of edges is 5p plus 6h, but they shared 2, so we have to divide by 2. The same kind of thing for the vertices, because they meet in 3 at that vertex. So when you do the calculation of the Euler characteristic, as we know it's called, f minus e plus v, miraculously, the number h disappears. And so you end up with a simple equation that p is 12. So there we go. Mr. Euler strikes again. So this is now the part of the talk that we're playing this game. Cherchez le pentagon. Here's an example of a Goldberg polyhedron, although maybe you didn't know that, because this is as you know, is a golf ball, and it has these dimples, which will be yet another talk, a very interesting talk as to why the golf ball has dimples. And this is the standard way to create them. You create them with hexagons. But wait a minute, you cannot do that with hexagons. It doesn't close. So there has to be some other shape, and these are pentagons. So there has to be pentagons in this golf ball. Not only that, there have to be exactly 12 of them. So where are they? Well, you're maybe too far away to see. So here's one. Here's another where you can't see, it's very blurry. And there's one over there, and so on. So if you actually, next time you actually have a golf on your hand and it looks like this, stare at the dimples and locate the 12 pentagons. All right, so here's, for example, a US patent. I somehow love these pictures from the US patent office, where they have to describe exactly what the object you're patenting is. And so this guy patented a design of a golf ball. And you can see right here, the pentagon. Oops. Okay. Now, as a mathematician, the first kind of thing you might want to say, okay, wait a minute. We have this string of polyhedra made out of hexagons and pentagons. How many hexagons do they have? And well, faces, total faces, hexagon and pentagons. So this is the icosahedron, yeah, this is the dodecahedron, right? So it has 12 faces. This is the truncated icosahedron. This is the soccer. So it's 12 faces plus 20. And then these are the numbers. So clearly, some numbers are missing. Mysteriously, all the numbers end with 2. So I can ask you, maybe, I don't know how good you are at pattern recognition. If you've seen this sequence before, can you tell me maybe what it is? Other than there's the number of faces in the Goldberg relatives. Yeah, I don't know how easy it is. You can put it in Sloan and maybe he'll tell you. So let's just cut to the chase. This is the number 10t plus 2. And t I'm defining to be this number, a squared plus ab plus b squared, where a and b are certain positive integers. So in other words, the sequence is built out of, for each pair a and b, you create this number a squared ab plus b squared. 10t plus 2 is going to be a number of faces in the sequence. So this number t, we'll come back to it, but is what virologists call the T number. It comes from triangulation. So this is a paper by Goldberg himself. So he wrote 2 papers, as far as I can tell, about this topic of this polyhedron. And this is the second one. I was going to say, and I kind of forgot to bring it up, but there's a specific reason he was looking at these polyhedra. He was trying to minimize something related to area and volume of polyhedra. He didn't just come up with the idea out of the blue. So here's the way he describes this. So here are the numbers. Each number in a circle is some polyhedron and what the number of faces it has. So down here is 12, 32, 42, and so on. So it's a graphical way to describe the formula I gave you before, because A is the axis going this way and B is the axis going this way. So A squared plus AB plus B squared is kind of the norm squared, the distance squares of a lattice point in a hexagon lattice. Right, that's kind of geometrically what these numbers mean. And what he mentions in this paper is 2 things that, but his interest was the following. Okay, no, I'll come back to that. So what do these A and B mean in terms of the polygon, of the polyhedron? So what it means is the following. Since we had 12 pentagons, then there is a well-defined, well, you have to choose what direction, but up to sort of what direction you go first with, is how many steps you have to make to go from one pentagon to the other. So this one is a 3-2 Goldberg polytope, because you go 3 steps in this direction and 2 in this direction to go from one pentagon to the other. And this is for any pair of closed pentagons, close in, you'll see the same number. So this characterizes the polyhedron, but only up to some symmetry, because, for example, if you take the first time that these two numbers are not the same, starting with small value, versions, which are mirror image of each other, so they're not really the same. So this thing is chiral. So you can go 1 step and 2 steps, or you can go 2 steps and 1 step, and you cannot go from one to the other by means of rotations. There's a mirror symmetry between them. Okay, so what is he interested in? Goldberg is the fact that in this array of numbers, some numbers are because this quadratic form a squared plus ab plus b squared it doesn't uniquely determine the number ab. I mean, it's sort of the distance squared to the origin, and there's going to be for various particular values of that distance, there's going to be several points on the circle. So the first time I think that happens is here, 492, where if you look at the numbers 5, 3, or 3, 5, of course, then the norm squared in the hexagon lattice is equal to 7 squared. Which means that, so what I won't get into this too much, but he describes, so what he does is say, okay, what we have is basically some kind of tiling that I can put down on the plane, at least locally, and it has hexagons and it has pentagons. So I can describe the polyhedron by those two numbers as to how you describe how many steps in each of these two directions you go to get from one to the other. So here's the 7, 0. So you just go 7 steps straight up from one pentagon to the other. Okay, and the other, so here's the 7 steps. And the other one is the 5, 3 choice, which you can go 3 steps. Well, I guess I did it backwards. 3 steps and 5 in my choice of direction being this one first. And so what he somehow was struck by, and he makes a big point that, in other words, the point of his paper is that these two polytopes with the choice of 7, 0 or 3, 5 or 5, 3 have the same number of faces, but they are topologically different. And he argues if you follow from this pentagon to the middle edge of a hexagon, you go, in this case, through the middle of 2 pentagons, and in the other case, you go straight to the next pentagon. So they're just topologically different. And for somehow he was struck by that. But intrinsically, what he's also describing is this pair of numbers A and B, and how you could possibly create the polytope, but by taking the hexagonal lattice and cutting out a triangle and using that information to build the polyhedron, which, as I said, I'm not going to get too much into it. So here's an example. For example, if you do the 2, 1 case, you create a triangle from the center by choosing, in this case, 2 steps in one direction and 1 in the other. So is this vector A. And then you create a triangle with this vector in the 3 directions, and then you somehow bring it back to the sphere, and that defines for you a Goldberg polytope. And the triangle in question here is the underlying triangle of the icosahedron, because this thing has icosahedral symmetry, so it has to somehow have the icosahedron included. All right, so let's move to the next thing, which is well, I'm calling it the Il Duomo. So here's apparently the first time that something like this was created. They call now geodesic domes. So you see this thing over here, which was a planetarium done in Germany in 1924. So these are all the people waiting in line to get in. And it's made out of pieces that look all pretty similar, and is making up something that looks like a ball. So it's this same kind of engineering problem. The other more famous construction of such a thing is this biosphere of the World Exposition in 1967 in Montreal, which I think is still standing. And this was the US pavilion in that World Fair. And it was really striking somehow as a feat of engineering and design and architecture. So here's another construction of the same kind. And now the reflex would be, okay, wait a minute, where's the Pentagon? And I didn't write it, but you could. I used to have a slide with the Pentagon, but now, so it's right here, right? This is one Pentagon. And the guy that was behind a lot of these geodesic domes was this American architect, Buckminster Fuller. And he was a very interesting person, in my opinion. And he made it to the cover of Time, although it's debatable what that means in terms of, you may not have noticed that the current president of Argentina made it to the cover of Time. So anyway, so he made it to the cover of Time, and here is his dome, which he is made out of triangles. And again, this is the same engineering principle. We want to make something like a sphere with the simplest possible shapes. And these are all triangles, which are all exactly the same. So for a construction point of view, architectural point of view, that's a very good thing. You create these struts that are all the same length. You have to put them together in the same way and then build up this sphere with them. So here's a pentagon, right? There has to be 12 of them. And here we see that the basic pattern of the Goldberg story, because we see triangles forming as a hexagon and triangles forming a pentagon. So this thing is made of triangles, but it's following the principle of the Goldberg polytope. And just for fun, I don't know if you ever encountered Fuller anywhere, but he was a very kind of broad visionary, and he wanted to design all kinds of things. So for example, he has this design for a car that somehow doesn't seem to have made it very far. And here's another concept that I'm not sure he introduced, but he certainly pursued and promoted, which again, some of this slide remains from the Italian version. In English, it's called tensegrity. Yeah, I think it's the word, not tensegrity, which is a mixture. It's a weird word which is made up, made of tension and integrity. And his proposal was to create structures that were put together and stayed together because of the mixture of a tension and repulsion somehow. So here's a way to create an icosahedron out of pieces of wood and rubber bands. And this thing stays together as it is. The tension of the rubber bands keeps it together, and the strength of the pieces of wood keeps it not sort of collapsing on itself. And here's a way, I never tried this, but I think it would be quite fun to try, to build it. Okay? And here's a sequence of pictures of how you could do it. I'm sure it's not easy because, yeah, it stays together once you put it together, but putting it together is probably not easy. All right, so here's another, this is up, at the time, I think I had not seen this before, but it's still standing somewhere in the US, is this needle tower by a sculpture called Nelson. And is, as you see, this is quite high and it just stays together by the tension between the wires that are pulling this struts together, and the struts are keeping it without collapsing. All right, and so here's something that explains or illustrates this very well. Okay, why not? Go back, see if it works. This seems a little hard to believe. So this thing stays together as it is with the tension of the chains and the strength of the solid pieces. Anyway, this is something that this guy was very keen on. And to me, the reason I bring it up, because I will try to move quickly now. There's two more topics that I want to touch upon. One is this fullerenes, right? As you may know the story, they're named after Fuller because these guys that eventually got the Nobel Prize in Chemistry for it literally discovered this molecule that is made out of carbons put together in this form, like this soccer ball. But when they found it by this procedure, which is whatever it is, you throw rays into something, into a whole kind of mix of molecules, and then you measure something. Sorry, I'm just very, very poor in my chemistry and physics. But the point is that at this height, there clearly is something happening. And this is what they said, okay, well, there's something there. And in this format is clearly something that has the number 60 attached to it. So they knew there were molecules of this random collection of carbons floating around in this stuff that they were measuring, that there was enough of the particles that have 60 carbons together to make this blip in the radar. But they didn't know how these carbons were put together, which is a little strange in a way, because you know, if you play soccer, maybe the first thing you think is, oh, it looks like a soccer ball. But it didn't go that way. I mean, it's a really fascinating story how they actually discovered what the shape was. And they were inspired by Fuller, by the Montreal dome. So one of them, I forget, I think Croto, yeah, had been to Montreal to the fair and remembered the Fuller dome, and somehow he thought, oh, maybe that's what it is. Now, since I think this website has been down, but Croto, which passed away not long ago, I think, had a website with a lot of stuff about this discovery, and he talks about his upbringing, and he says that he basically never did anything of any good until he discovered this molecule. And in particular, when he was a kid, nobody gave 2 cents for him. I mean, and so he was born in Germany, I believe, and moved to the UK. And the teacher, I don't know what grade this was, but probably elementary school, wrote a letter to the parents, and her comment was, he is very fond of play. Well, maybe that's why he discovered this molecule. Anyway, let's move to viruses. viruses, now here to me is the most interesting thing, a more intriguing thing of this whole thing. Because let me just move forward and tell you what I mean. So here's this one of the first papers. People did not know how viruses look like. They're very, very small. And they just didn't know what kind of structure they had. So Watson and Crick, the guys who discovered the shape, the structure of DNA, were interested in this. And the only tool that they had basically is that these viruses somehow crystallize, and they can do crystallography and look at them as if they were crystals. And so they wrote this paper about the structure of small viruses. And I want to highlight these two parts. So the purpose of this article is to explain this observation by means of the following simple hypotheses. The observation being that they look like either rods or spheres. A small virus contains identical subunits packed together in a regular manner. Well, we heard that before. Our hypothesis is that in both cases, the rod of the sphere, these shells are constructed from a large number of identical protein molecules of small or moderate size packed together in a regular manner. So the viruses have exactly the same engineering problem that a football player has. How do you create the ball you're going to play with? And here's a summary of something he said in a conference. I saw it quoted in a different sort of historical paper. There is not enough information in the viral genome to encode a large number of non-identical protein subunits. And the word that really intrigues me here is information. So these things, as dangerous as they are, as we well know, have very little, as a very small, very little amount of information to them. So they cannot create an Alhambra type design of their outer shell. They have to create something that is very simple because they just don't have enough information to create something sophisticated. That's my understanding of what they're trying to say. So then these two other guys, Kaspar and Klug, went a little further, because what Crick and Watson said is that these subunits can only be 60 of them. Basically, they were saying they can only be the 60 pieces of a icosahedron, where you take the 20 faces of the octahedron triangles and break them into 3 equal parts. Or 60 is the size of the group A5, so you can think if you have some shape in your object, then you can move it around with the group, and if it doesn't repeat, you'll just get 60, an orbit of size 60, and the thing can only divide itself into orbits of size 60 or some divisor of 60. So they thought, or they proposed that the viruses were made out of 60 different, so the same unit repeated 60 times. And they were not quite right, but they were the first to say anything sensible. And this whole story is also, I think, fascinating, because the crystallologists, the chemists, were really skeptical. In particular, because they were using crystallizations of the viruses, and they were claiming that there was a order 5 rotation, and it just cannot happen in a crystal. So they probably just thought that they were just completely off the wall. So what they thought is, okay, well, maybe, you know, how do we, so the thing is that then they discovered that there were viruses that had more than 60 subunits. And so the theory wasn't quite right. How do you fix it? So here's what they say. There are 2 key facts about viruses from where all considerations of their structure and functional organization must proceed. The first is that the essentially infective agent of all viruses is a high molecular weight nucleic acid component, DNA or RNA. Second, the nucleic acid molecule is contained in a protective package which serves to transmit the infectious agent in a functionally intact state through space and time to a susceptible host. So basically, I read this to say, viruses are a soccer ball with stuff inside. And the stuff in this thing that covers it has to be made by very few elements that repeat in some way. So here's examples of, these are reconstructions of various viruses, parvovirus, human hepatitis, dengue, Norfolk virus. And you can see already that this thing looks very much like the other things we were discussing. Unfortunately, they exist. Okay, so I think this, I'll skip it because it would need more discussion. So, okay, maybe just say quickly a word about. Basically, I don't even know that they quote Goldberg because they basically rediscovered what Goldberg had done. What Kasper and Klug say is that they relax the idea of a strict symmetry, that all the faces have to look the same, and you can allow, they call it quasi-symmetric, and they basically are allowing shapes, a few shapes to be there, not just exactly one. And they end up exactly in the Goldberg situation, and they define this number t that I told you before, a squared plus ab plus b squared, and they call it the triangulation number because it is something like this. If you, so for example, t equals 1 is that the original icosahedral face, you divide it into 3 parts. T equals 3, you divide it into, well, this is 1 part, but it has these 3 different colors. This is 3 parts, this is 4 parts, 7 parts. And then this is basically how the construction of the outer shell of the virus looks like. And these are the various proteins that make it. So this T became known as, I said, the triangulation numbers. And if you, apparently they still, although things have evolved and they discovered that this wasn't quite a complete theory and things needed to be done a little better, they still use in the literature the T number of a virus. So if viruses are classified by T numbers, but the smaller the T, the simpler somehow the structure is. But I haven't traced this whole thing sufficiently, but it seems that they never mentions Goldberg. So I don't quite know what happened there. It might be one of those instances where math, for its own intrinsic reasons, did something that people later rediscovered for their own reasons, and they never connected the two things. Okay, so I think that's all I wanted to say with a nice, this is what we all want. All right, thank you. Yeah. Yeah. Yes. I think it does. I mean, as I said, I mean, I looked at this because I like it. I might say something slightly wrong, but I believe that there are other molecules, it's just a lot less stable. Even creating the actual buckyball by itself, I think it was a big deal. It came later. And I think the others show up, but they're much less stable. But yes, I think there is another little bump, which is the next, is a next structure, yeah. Well, that could have been a ball and it wasn't. That's what you want? The one, yeah. The 2-2. I think it's the Goldberg 2-2. The soccer ball is 2-1, and the other one that looks like it could be is 2-2, I think. Here. This one, you mean? You mean the actual football? Okay, we'll get there. Ugh. Here. Yeah, this one. I think it's an interesting question. I don't know. I mean, I think that the level of sophistication that goes into these things has become amazing. So who knows? And presumably they didn't realize that before. And maybe in very special circumstances where the kicks were a particular speed, a particular force, the thing behaved weirdly. I would be surprised, I have no idea, but that they hadn't realized and they said, okay, we'll do it anyway. But the amount of money that must go into designing this thing must be enormous. And as I said, there must be competition too. It's not like, I don't know how it works, but I suppose it's not a given that one company is the one that always does it. And even designers probably compete very strongly to be able to design the ball. I think I had another version of this talk where I mentioned this thing about, well, why is it, for example, that, so the first ball in 1930 was created with these pieces of leather. It looks like really poorly done, but inadvertently, it had a feature that made it a good ball, which is that it's not smooth. Right? Yeah, I guess this you probably know much better than me. I mean, if you ever were a kid with a ball in the beach, you know that the beach balls are terrible, and because they're completely smooth. And so you do need, that's why the golf ball has dimples. And Philip Candelas told me that this is something that's known, that people in Scotland, when they started playing golf, sort of naturally started always choosing old balls to play with, because the old balls, they were made of wood, and after a lot of games they started to deteriorate, but those flew better than the new balls. And so eventually they realized, oh, wait a minute, there's something here. And so you need to have a rugged surface, because otherwise the turbulence behind it makes the ball actually go slower. So there's I don't know, there's a lot of sophistication into how the ball actually flies when you kick it, and they have to do it within the range of what players manage and so on. So I don't know. Yeah, it's a long non-answer to your question. Thank you very much.